Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. It's my pleasure today to welcome two visitors from the University of Illinois, Saru and Vikram, are both here for today and tomorrow. And so if there are other people who aren't on the schedule who want to talk, there's a little bit of time. But it's my pleasure to welcome Sarup, who's going to be giving the talk today about some work he's been doing on debugging frameworks.
Thank you. Thank you. Good afternoon, everyone. So the title of my talk is towards developing a automated debugging framework and using automated software fault localization by filtering likely invariants. This work was done along with my colleagues Vikram Adbe, John Criswell, and Chase Gagel at University of Illinois. Okay, so the broad goal of our work is to develop some kind of automated or semi-automated system to help programmers or developers fix bugs. Okay. And let me give some motivation for our work. According to a NIST report, software failures cost nearly $60 billion of losses every year. And large applications contain, so widely used applications contain large number of bugs. For example, Mozilla, they get nearly 300 bugs every day. So they need some kind of help to probably triage and diagnose these bugs. Okay. And it's also known that cost of fixing bugs increases exponentially as the software development life cycle progresses. So bug fixing costs are very high during operational or maintenance phase. So it's very important to quickly fix as many bugs as possible before the application ships and gets deployed. Okay. And the process of debugging involves three key steps. First is reproducing the failure, then trying to locate and understand the root cause that is responsible for the failure, and then finally trying to fix the root cause. And debugging is a complex job for many reasons. Reproducing the failures may be very difficult in many cases. And the point of failure may be very far off from the root cause, and that kind of complicates the process of debugging. And hence debugging is mostly a manual and time consuming process now. And automatic fault localization, which mainly focuses on the second step. Okay. And it can automatically identify the root causes or the program statements that is responsible for a failure. And it can also extract other valuable information that may help the programmer debug or find or fix the bug. And automatic fault localization can reduce the development cost and time significantly. So the broad overall goal, our broad overall goal is to develop some kind of automatic or semi-automatic system to help programmers fix bugs. Okay. And one great example where such a system can be applicable is during software testing. Okay. Doing any kind of automated software testing, which takes as input program, test inputs, and expected output, and produces failing tests. Okay. So they have all the ingredients that is required for a automated debugging framework. Specifically, all the failing tests have some kind of oracle to say whether, which can detect whether some input actually, whether the program fails on some inputs or not. Okay. And using all this information, an automated debugging tool can try to point out possible locations of root causes and some other also informations like faulty program values, faulty execution paths, and the cause effect chains which produces the symptom. Okay. And all this information can be greatly valuable for fixing and debugging and fixing bugs. Okay. In particular, currently we have worked on actually trying to localize the faults. In one of our recent ASPLOS papers, we developed an automated system to identify the root causes of the failures, and it was very scalable and it reports very few false positive. And our tool takes program and faulty input as the input, and tries to produce the faulty locations in the program in some way. It also provides some other very valuable information, though we don't yet present them or output them in a presentable way. Okay. So our technique is based on many basic techniques. One of them is the well-known popular Delta Debugging strategy, which tries to compare memory states of two different runs to isolate the root causes. However, it's pretty expensive to do that. And likely program invariants can be a very efficient way to compare, to summarize and compare memory states of different runs. Okay. And what are likely program invariants? They are program properties which are observed to hold true for some set of successful runs, but unlike sound invariants, they may not hold true for all possible future runs. For example, we can say return value of some function is always positive, or some stored value is between 0 and 100, or some load value is always 10. These are some kind of some examples of likely invariants. And all the likely invariants that fail during the failing run can give us a set of candidate root causes. But even if after this step we need still lots of improvement for actual effective fault localization. So some important contributions of our work was that we used a novel mechanism to train invariants. In particular, we use automatically generated similar input which are close to the failing input to generate these invariants. And we combined our approach with the dynamic slicing, dynamic backward slicing in software. And we used two novel heuristics for reducing the false positives further. And we use many bugs in 4 large applications like Squid, Apache, MySQL, and Clang for evaluation. And we got around 5 to 28 locations as candidate root causes, even for programs of like 100,000 to 1 million lines of code. And after that, we applied some trivial manual filtering steps, which gave us only 2 to 14 program locations. And in many cases, we had only 2 to 4 locations. Okay. So the results were excellent. So, yeah, sorry.
So what does the root cause mean? Does it mean that you can change these instructions to?
Yeah, it's kind of that. Okay, I guess formally root cause are any program statements which are responsible for the failure. But for evaluation purposes, we saw the patch which statements were changed to fix the failure. So for evaluation, we use only those statements. We call those statements as root causes. And I guess, yeah.
Programs.
Yeah, some are multi-threaded, though we don't have any concurrency bugs right now. Okay. Some of them are multi-threaded. Yeah.
So how large is your final report? It's a program slice or just several statements?
Several statements. Maybe I'll show the statements, yeah. Some results I'll show, yeah. Okay. Okay, so I gave the motivation and contribution of our work. And now I will be talking about some problems with the existing fault localization work which we try to address. And after that, I will give details of our bug diagnosis framework. Then I will give some key experimental results. Then I will talk about some of the future work we plan to do towards developing a usable automatic debugging tool. Okay. So before going further, I will give some definitions which I just talked about the definitions. So we define all the faulty program statements that are responsible for the failure as root cause of the software failure. And for experimental evaluation purpose, all the modified statements in the patch, we call them as the locations of true root cause of a software. And all the candidate root causes which are not the true locations of the root cause, they are called false positives. Okay. Yeah.
They modify 10 locations and you find one of them, is that a success, or you need to find
no,
all 10?
No, we have to find all 10, yeah.
You need to find all
Yeah.
10?
But only out of them which are really actually, sometimes they actually try to fix other things and some are irrelevant statements. So So if it finds out all the relevant statements that needs to be changed, then we call it success. Yeah, but it needs to find all of them. So there have been already a lot of work on automatic fault localization, and we have classified them into 6 categories here. Okay, and I'll talk about only first two which are most relevant to our work, and if any of you are interested, then I can talk about anything else. Okay. So, so delta debugging is a very popular work for fault localization, where it's a smart approach which compares different memory states of different runs, but doesn't scale well. And there have been some improvements to delta debugging so that it can handle larger applications. And this aims to find fault cause effect chains, but in many cases, still in 55% of the cases, it can still miss the root cause. And as I said, invariants is a good way, is a compact and precise way to compare different runs. But most of the previous work, I think all of the previous work have many issues. First, the test inputs they use to train the invariants may not always be available, and coverage of test inputs is often low for training. Okay. And they don't have any solution to make the likely invariants narrow or tighter. So when the invariants become very broad, so the root it may miss the root cause. Okay. So some of the key insights of our work, which tried to improve upon the previous work, was we use likely invariants as a compact or precise way to summarize and compare different runs. Okay. And in this way, we can quickly isolate the difference in behavior and give the programmer an initial set of candidate set of root causes. And we, instead of using general test inputs, we automatically generated similar closed Squid inputs to train the invariants. And because of this, we can now use very few closed good inputs to train the invariants. And because of this, we get much more tighter and relevant invariants. So we have very few false positives. That means we don't miss, false negatives. That means we don't miss many root causes. But this may result in many false positives. And hence we developed a sequence of novel filtering techniques to reduce this false positive set to a much smaller set. Okay. Now let me give some more details about a bug diagnosis framework. So this is the overall architecture of our tool. Our tool takes program the original bad input and an optional input specification, and then it uses them to try to generate many similar inputs, many similar good inputs, and these good inputs are used to generate the invariants, and these invariants are then instrumented back into the program. Then it is run with the bad input, and after that all the failed invariants will give us the initial set of candidate root causes. Then we apply a set of false positive filters to reduce this set of initial candidates to a much smaller set. In particular, we apply 3 filtering steps. First one is dynamic backward slicing, second one is dependence filtering, and third one is multiple faulty input filtering. And I will talk about them in a little more detail later. Okay. So let me give a concrete example to explain some of the concepts later on. So this is a bug from MySQL, and this bug happens when an SQL query uses a specific date field with year value as 0, and this causes a segmentation fault in MySQL. Okay, and the segmentation fault happens at line 7. Okay, when the weekday value becomes negative, and this results in a buffer overflow. But actual root cause actually starts in at line 3, where an unsigned year value is used, and because of this, when year is 0, year -1 becomes a very large value instead of -1, and this value propagates through various intermediate values, and it then goes to the DNR value. Then DNR is used, and this value propagates to weekday, and finally weekday becomes negative, and it results in segmentation fault. Okay, what I showed is a kind of simplified version of the code. Actually, this code is split across 3 different functions, okay, and this is where the buffer overflow occurs at line 16. And there is a function which computes the weekday value I showed in the previous slide, and there is another function which computes the DNR value I showed earlier. Okay. And the faulty values flows through the green arrows here. Okay. And I will use this example to illustrate some concepts later on. Okay. Now, diagnosis with invariants. So in this work, we use likely range invariants to find potential root causes. Okay. And what is likely range invariant? Likely range invariants are a range of values which are computed by individual instructions in the program in the correct runs. Okay. And when these invariants get violated during the faulty run, they give us the set of initial candidate locations. Currently, we have invariants only on load values, stored values, and the function return values, since they are the most critical locations. These are some of the examples of the invariants kind of. Here this is so return value of weekday is between 0 and 6, and here some load value is always positive, okay, and here store value is always 100. So these are some of the example invariants we can use. In the source code example, we have invariants on the return value of these 2 weekday and DNR functions in line 9 and 12. Okay. And here the invariants where return value is always positive, and these actually fail during the faulty run. Okay. And they give us kind of initial set of candidate locations. One important point to note here is that we are not actually trying to observe invariants on intermediate program values. Like for example, let us say del sum or any other or temporary value here. So the bug may be actually anywhere in those intermediate values which feed value to the function return values or the invariant instructions. So when we present the result, we give all these statements also, we output all these intermediate statements also, we give them to the programmer, since the bug may be anywhere in the expression. Okay. And we call this actually expression tree of the invariants or the return value. Okay. As I said earlier, we train invariants using very similar inputs which are close to the failing input, and which in this way we can capture the key relevant differences between different runs. Okay. And because of this, we use very few inputs to train the invariants. We get much more tighter and relevant invariants, and we are less likely to miss the root causes, though it may result in many false positives, and we have many false positive filters for them. Okay. Okay, I will briefly talk about how we construct inputs, and one important point is this may not be the best way to actually generate inputs, though these techniques work. And one of the key reasons of we visited here is that we want to really would like to collaborate with kind of testing teams like SACE and PEX who are doing dynamic symbolic execution and probably other tools, and using them probably we can have much more we can generate the inputs in a much more systematic manner. Currently we have 3 approaches to generate inputs. One is deletion based specification independent approach, which is kind of variation of the well known DDMIN algorithm, and where we try to apply character level deletion. And the second approach is replacement based specification dependent approach, and for this actually we need some kind of input specification, like which specifies what are the lexical tokens that are present, that can be present in the input, and for each token what are the alternative set of tokens that we can replace them with. So depending upon the token type, we try to create many variations of each token, and then we combine one token at a time to create the inputs. And the third one was for compiler bugs, we use a C-reduce based approach. So C-reduce is a tool which tries to automatically create minimal test cases for compiler bugs, and while it does so, actually it produces many similar inputs along the way. So we actually modified the test scripts in the C-reduce tool to keep track of the good and the faulty inputs and classify them accordingly. Okay. And then after that, we can actually select a small set of inputs which are close to the original failing input. And I have some if anyone wants to know more details about them, I can actually explain later. Okay. So right now what we have is we have a set of similar inputs, then we select a few close good inputs from them, then we generate invariants using those good inputs. Okay. And then what we will do is we will insert those invariants back into the code and run it and run it with the bad input. Okay. Now the failed invariants will give us the set of initial candidates. Okay. Okay. But we still have hundreds of candidates after this step. Okay. It's a significant reduction, but still is too much for the programmers to analyze. Hence we apply 3 different filtering techniques. First is dynamic backward slicing, which tries to remove any kind of candidate invariants which may not be influencing the symptom. Then we apply something called dependence filtering, where we try to discard the dependent failed invariants if there is no intervening passing invariance between 2 failing invariants. And third is multiple faulty input filtering, where we run these techniques for many different similar faulty inputs and then try to take an intersection of the candidate root causes from all such inputs. And I will talk a little more about them now. Okay. First is dynamic backward slicing. Here we try to build a dynamic backward slicing starting from the failure symptom, and any invariant instruction or any initial candidate root causes which does not fall under the backward slice, we remove them. We implemented the NPWC algorithm in 2 phases, and we handle both the data flow and control flow dependencies. And at the runtime we record all the memory locations accessed, all the basic bugs that are traversed, and the function call and returns, and build a dynamic program dependence graph using this trace in the SSE form. And this tool, what we call it as Giri, and is available as open source, and other people are using it. And also there is a Google Summer Code Up project this year, where we are trying to actually make it more general and widely available. Okay. And we compute this dynamic backward slice on the original failing run, since the root cause is likely to be in the failing run. And in our example, the 2 invariants which were on the return value of day nr and weekday function, they lie on the dynamic backward slice, so they are not filtered out. Okay. Now let me talk about the next filtering step, which is dependence filtering. So the main idea here is that the return value of the day nr function is actually used by the return value of weekday function. Okay. So the fault, in this case we say that this value actually failed, not because this is faulty, but since it used a faulty value from the previous dependent instruction. Okay. So most likely the root cause is here, not here. Hence, actually, so we say that this is a possible root cause because the return value, the invariant return value greater than or equal to 0 got violated here by a negative value. But this one is probably not a root cause, so we can probably filter this out. So in general, the idea is we go through the dynamic we go through the dynamic program dependence graph, and we check for invariant failures. For example, if a failed invariant uses value from another failed invariant, okay, we say that the dependent invariant actually is probably not a root cause. It only failed because it used a faulty value from the previous invariant. So we can filter this out. In other cases, when there are passing invariants between two failing invariants, in those cases we don't filter this dependent invariant because it used a value from a passing invariant. So our assumption is that this value is correct. So this used a correct value and it fails. So this is also a likely root cause. So in this case we keep both the root causes.
So why didn't you eliminate the top one?
Oh, eliminate the top one?
Because it looks like it's sort of, the code seemed to have recovered from that root cause, right?
Yes, that it may have recovered, and one more thing is actually we are seeing one path. It might be going through another path to the other to a symptom. That's one important reason. And I guess in some, this is actually not also a sound technique. Our filtering techniques currently are not sound. So it's possible that actually, as you said, this may not be a root cause also, and it's possible that this may not be also root cause. Actually, this is a root cause. Okay, so our technique is currently not sound. So it's possible that sometimes it can filter out the true root cause. Yeah, but in this case, we don't know if it may be going through other values too and reach the and maybe affecting the symptom. And multiple faulty inputs filtering step. This is a very simple idea. So we assume that root cause is same for all the similar faulty inputs which cause the same failure. Okay. So we assume that the root cause must be present in the candidate root causes of all such inputs. So what we do is we use the similar input generation methodology to create many similar inputs, okay, and we repeat the previous 3 steps to construct many different the candidates root causes for each different input. Then we take an intersection of all those candidate root causes, which gives us the final set of candidate root cause locations. Okay. Any questions? Okay. Now I described some of the key details of our bug diagnosis framework. So I will talk about some experimental results, key experimental results now. So here I would like to address 2 key important questions. First is how effective our overall bug localization framework. Second is how effective are our filtering techniques. Okay. So for the experimental evaluation purposes, we use 13 bugs from 4 applications, and there were 5 bugs which were missing code bugs. That means there are some parts of the code which are missing, and we didn't consider them since our framework currently can't handle them. So we need kind of additional kinds of invariants like control flow invariants to handle them. So we didn't consider them for this evaluation, and we used LLVM for compiling programs and running our parses. Okay. This table gives some key characteristics of the 8 server bugs. From the server bugs, we use 3 server applications: Squid, Apache, and MySQL. And The third column here gives total number of static lines of code that are exercised by the faulty run. Okay. So we have around kind of thousands of lines of code that gets executed. And the fourth column gives the distance from the root cause to the symptom in terms of number of dynamic number of LLVM instructions. Okay. And this column gives the distance in terms of number of static number of lines of code, and this gives the distance in terms of static number of functions from the root cause to the symptom. And the important observation here is that there are thousands of lines of code that gets executed in the failing run, and the distance along the slice from the root cause to the symptom spans several functions, and this distance is especially high for the incorrect output bugs. So for the incorrect output bugs, there are kind of tens of functions between the root cause and the symptom. And for such bugs, I think it's diagnosis process is more difficult. Okay.
So if you just did a dynamic slicing, how close those distances become?
This distance is showing along the dynamic slice, I think. Oh, sorry. Oh, this distance, right? Yeah, this is along the dynamic slice actually. Okay, I have not included the other instructions here. Okay, there may be other irrelevant instructions. So if you take the slice from the symptom to the root cause, so it will span through this many functions.
And what is the input for these applications?
For the buggy input?
What does the input correspond to? Is it a buffer or is it data structure?
Oh, for these like MySQL is kind of some kind of query, like I showed the example MySQL query, and for Squid and Apache, there are some kind of HTTP requests, HTTP or FTP requests. So we take the inputs to the application. Okay. So now let me talk about how effective was our overall bug localization framework. Okay. If you see, each of these bugs exercise thousands of static invariants, and when we run our invariants pass, so we had around hundreds of failed invariants in each of those bugs. So we can see it's a kind of significant reduction from thousands of invariants to hundreds of invariants, but I think it's a lot more for the programmers to analyze each of them and figure out the root cause. And when we apply all the three previous filtering techniques, we got around 5 to 28 program locations as candidate root cause. So the filtering steps were quite effective. And then what we did was we actually manually went through those root causes, and we applied a trivial filtering step there, which I'll talk a little bit later. Okay. Then we could reduce it to only 2 to 14 program locations. So overall, the approach was pretty effective for these bugs. Okay. And we missed root cause in one of the cases. And here the root cause was, so inside the visit function, we set the skip process uses to false, and we call this visit expression function here. And here the condition in this branch was wrong, and hence it didn't set the skip process uses to true, so it remained false, and it comes back and it incorrectly calls the process uses function, and it results in a assertion violation. So to handle this kind of bugs, we will probably, there are several ways to tackle this. First is we can do a better input generation so that it clearly differentiates the failing runs from the good runs, or other kind of invariants may help here, like control flow invariants, and also invariants on the intermediate values. Right now, as I said, we have only invariants on the function return values, loads and stores, not on the temporary intermediate values. Invariants on intermediate values can also help in such cases. So and that's the kind of future work for us. Yeah.
What do you mean by control flow invariants?
Control flow invariants, by control flow invariant means I mean any kind of general invariants which takes into account which branches the program take. One example is I can think of is kind of diffuse invariants. So people have so basically if I have some use, which definitions it is using, so that depends on the control flow of the application. So this kind of invariants. So for some classes of bugs, it may be pretty useful. For example, like missing code bugs, this can be useful. Now, now how effective were our individual filters? So if you see the slicing filter, so it's pretty effective. It was able to reduce nearly 80% of the false positives. And the second was dependence filtering. It was also pretty effective and reduced nearly 53% of the remaining false positives. And the third one, multiple faulty input filtering, was somewhat less effective. It reduced 14%. Still, I think we can say, since it appeared after a set of very effective filtering steps, also this is still a significant improvement. Now, one important thing was for one of the bugs, the last filtering step actually missed the root cause, since for some of the faulty inputs we generated, it didn't contain the root cause. And so finally, the last step actually we had the root cause for 11 out of 13 bugs.
So did any of these fixes change the control flow of the failing test case, or were they just?
Sorry, can you repeat that?
Did it change the control flow of the failing test case in any of these bugs?
After fixing?
Yeah.
Control flow. Yes, some will, not all, but some of them will change the control flow. Yeah, for sure. Yeah, but I don't understand. But sorry, go ahead.
If I understand right, slice and dependence filter are dependent on each other.
Yeah, it's somewhat. Yeah, dependence filtering actually uses the slicing step. Actually, the dynamic program dependence graph that is built during this.
Does not.
No, multiple independent. Yeah.
Did you evaluate that by itself?
No, we applied these previous steps on all those faulty inputs and took the intersection. So it.
Apply directly on the input and see how effective that one is by itself.
Oh, just by itself, you mean? Yeah, that we have not tried. Yeah, that's we can see. Yeah, it may be much more effective than if we applied at the end. Yeah, right. Okay. Now, so I'll a little bit talk about the manual filtering step we did. The programmers can actually manually look into those root causes and quickly try to filter out false positives. For example, when we looked through the candidate root causes, we found out that invariants in many we didn't do any kind of sophisticated processing. We just looked at the function name where those failed candidates invariants were. By just looking at the function names, we could figure out that they are very less likely to affect the root cause, less likely to affect the symptom. For example, lex and parsing functions. Actually, many candidates there will fail if there is a slight difference between the inputs, but it's kind of very less likely to affect the input. Same is the case with the input-output functions. Also for random number generation, they can randomly get violated without really affecting the symptom. And we also observe that many time-related functions fail, and they can fail if you run them in different times or something. So, but very less likely to affect the root cause. And this step actually did not eliminate the false positives. So after applying this, actually, from 5 to 28, actually, we could reduce them to actually 2 to 14 locations. And this is actually one of the bugs, actually, the candidate locations in one of the bugs. And here I have simplified them to just include the function names here. So first, actually, we can remove all the candidate root causes because of time function. Then I remove the candidate root cause for the random. My_rand is some kind of random number generator in MySQL. then there were two functions which were actually input output functions, and there were finally two functions which were lexical analysis, lex and parser functions, and after that we had only 3 candidate root causes here, okay, and the root cause was in this function.
How come you're generating invariants on random number generators in the first place? Right? And by default, you would expect there's no invariant on the return value.
Oh, okay. You mean there shouldn't be any kind of invariant there? Yeah, but since we are not doing it kind of we are not using sound static analysis. We are doing it at the dynamic runtime. So any kind of value it observes there, it will try to form some kind of range there.
So if you ran it long enough on good inputs,
Yeah, it will come out with something, but it's probably not a really valid invariant there, but it will come out something. Yeah. Okay.
It's also like invariant is really a bad term here. It's more like a observed range of values in some small number of runs that are close to the failing run. It's not an invariant in the
Object
sense
properties.
of
No, I
program
get
property
that.
and all.
But I was surprised that even you saw these dynamically generated properties.
We can construct a range for anything. Right? That's really all that's happening here. You run something 10 times or 100 times, you get a range. That's the range we use.
So, okay, so I'll talk about some of the, okay, so let's say, okay, for one of the bugs like the Squid length bug, okay, it worked in our case, but if you use kind of general test inputs, it may not work. So why? That's because the input field in the faulty input actually uses many special characters to reproduce the failure. And if you have any larger username in the training set than the faulty input, it will actually miss the root cause. For example, in this case, the failing input was something like this, where it had many specific special character in the input. And if you have in the training set, if you include kind of many different inputs and you have kind of some kind of very large inputs, it will fail because there were some invariants which were based on the lengths of the parts of the input. Okay, and this will become very broad if you use kind of many different large inputs. Okay. But our approach is kind of more likely to find the root cause in this case. Okay. Some of the caveats about our work. First thing is I talked about the expression trees, so how we output to the programmer. Second is input sensitivity. So, we output to the programmer all the failing candidate set at each filtering step. Okay. And for each candidate set, we also include the maximal local sub-expression tree rooted at that candidate, which includes all the intermediate values that feeds value to the invariant instruction. Okay. And we do this since we only track the load store values and the function return values, not the intermediate values where the bug may be actually. Okay. So as I had shown earlier, actually for this return value, for the invariant on this return value, the expression tree will include all the statements that are marked in red. And for the number of candidate root causes we had in our last filtering step, the total number of lines of code that which the source expression tree maps is here. Okay. And these numbers are somewhat high for some of the bugs. However, I think we can actually reduce this size of the expression tree to a much smaller set by putting invariants on the intermediate values and using some other more invariants like address-based invariants and the control flow invariants, because when you form the expression tree, actually the values can actually escape through the addresses and make the expression tree large for some of the candidate root causes. Okay. And also we observed the bug behavior was somewhat sensitive to the inputs we use. Like for example, as you saw in one of the bugs, the root cause, we missed the root cause in the last filtering step because of some of the similar faulty inputs we used. Okay. And the another bug, SQL convert bug. in one of our earlier set of experiments when we used manually generated inputs to train the invariants, it had missed the root cause, but in our automatic setup actually it did not remove the root cause. Okay. So, overall why does our approach work so well? So, we had initially few thousand static lines of code which were exercised by the faulty run, and our tool was able to reduce that to 2 to 14 locations. Okay. So, some key regions where I think the likely range invariants were effective for comparing runs of comparing successful and failing runs of many bugs. Okay. And we use few similar inputs to train the invariants. So, we had very tight and relevant set of invariants which avoided the false positives. Sorry, I have been talking about false positives more. So, which prevented false negatives, and we also had some very effective filtering steps to reduce the false positives. Okay, now let me talk about some of the future work we were planning to do towards developing a really usable debugging tool. Okay. First of all, our analysis already actually extracts many useful information. For example, the failed invariant and its value can be very helpful in debugging, and the bad inputs and good inputs also can and their differences can provide crucial clues about what the root cause might be. For example, when you observe the year field is always 0 in all the bad inputs, that will give some strong clue. For example, in one of the bugs, the parameter to the aggregate function was always negative to reproduce the failure. I think such information can be pretty helpful. And we also have the dynamic execution path from the invariant failure to the symptom. Okay. And all this information will be pretty useful. And we can additionally use some custom but simple static analysis to extract more information from the symptom invariants and execution path. For example, we can do some kind of symptom specific analysis. For example, memory bugs have kind of some specific particular type of root causes. So, if we can do some kind of symptom specific analysis, so we can probably pinpoint the root causes better. And second thing is white box false testing uncovers a large number of bugs. Okay. And today it's difficult to find out which bugs to fix, which bugs not to fix, okay, and how. And diagnosis can actually significantly help to decide which bugs to fix. Okay. And in such a case, in such testing environment, for example, like in a nightly testing environment, our tool can be much more practical, because one of the problems which our tool is, we need some kind of detector to find out whether input causes the failure or whether it's a good input. Okay. So, especially for incorrect output bugs, we don't have such a detector. So, we currently use some other versions of the applications or some other similar application to compare the output and to find to detect whether it's a failure run or not. Okay. However, in the nightly testing automatically provides us with a easy detector for all the bugs, and also it gives us a buggy input. So, this can make our tool really practical. And also we plan to pursue many future research directions to make this tool really usable and to kind of really pinpoint the root cause. First is our current input generation is not really general. Okay. So, we plan to do some kind of robust input generation, and also our filtering techniques are not really sound. Okay. So, we are planning to do some kind of more robust filtering steps, and we want to explore a broader category of invariants. Okay. So, currently there are many testing tools, automatic testing tools like SACE, PEX, etc., which uses that type of approaches and uses constraint solvers to construct new good and bad inputs. Okay. And such techniques can be leveraged to build a more robust general and automatic input generation for our framework. Okay. However, there are some crucial differences. For example, we need a search strategy which can quickly search execution path for similar inputs. In contrast, the existing tools, the testing tools, they try to explore different paths so that they can increase the code coverage. But our goal is kind of the opposite. Okay. And we also need a selection strategy to increase the likelihood of finding the root causes. Okay. And I have some examples regarding how we can do this. For example, in this bug, so the root cause was here in the last return step. And there are two conditionals here actually in this function. Okay. So if the C1 to Cn are the path constraints on the conditional to reach to this function, okay, and we can actually combine the other two conditional statements here, and now we have a complete path constraint up to this candidate root cause. And we can try, if we try to negate a certain constraint and solve up to that constraint, we can get a new set of inputs. For example, if we invert the last constraint here, okay, and each of these conditions here is a branch condition through which we reach the particular point. And if you solve these constraints, the solver may be able to give a different input here which is not a failing input, but probably a similar input to the failing input. Next we can actually try to negate the previous constraint and try to solve, and the solver can give us another input here which is similar to the previous input. But as I said, our goal is to actually explore similar paths, not increase the block coverage. So the search strategy will need to minimize the differences, not the other way around. Okay. Next one is building a more robust filtering step. We are trying to investigate use of dynamic symbolic execution to reduce the false positives. In particular, given a failure inducing input and given a failure inducing input and a particular statement, is there a different value of that statement which can avoid the failure? So we would like to ask this to the constraint solver. Okay. And depending upon the answer from the solver, we can categorize them into three different sets. The candidate statements for which a different value can avoid the failure, and some candidate statements for which no different value can avoid the failure, and third, the solver actually may not find any solution within certain time durations, certain time bound. And this may be, if such an approach may not be actually possible if we try to apply that on the whole program, but if we have a small set of candidate locations already, then this may be a feasible approach. And one issue here is the scalability issue because the execution can diverge from the point from where we change the value at the invariant location, right? So the execution can diverge, and you can possibly use the successful and failing runs to control the scalability. Okay. For this example, actually we can give some set of constraints like temp is equal to DNR plus 5, which kind of, sorry, okay, DNR plus 5, okay, sorry, yeah, so here it was computing DNR plus 5, okay. So this constraint kind of models that statement. Then this statement actually models the cast from temp to int, and now we have a condition which says the array index actually lies within the array bound. Okay. And depending on if the solver actually finds a solution, which it finds for this case, then we can say that this candidate this is a possible root cause. Okay. And if the solver can't find the solution, we can filter them out.
This sounds like this angelic debugging approach by.
Sorry, pardon me?
This sounds like this angelic debugging approach by Satish Chandra and a couple of other folks.
Okay.
They have a similar approach.
Similar approach? Okay.
Yeah.
Take a look at that. Looks like it's based on
Yeah, I looked at. Yeah, I don't remember if it's similar. Yeah.
We should take a look at it.
Yeah, you can retake. Yeah, we'll look at it. Okay, the tool can automatically identify the 5 to 28 candidate root causes, and likely range invariants were effective for comparing runs. And we had very few similar good inputs to get the tighter invariants, and we had novel filtering techniques to effectively reduce the false positives. And after we applied the manual filtering step, we had only 2 to 14 candidate locations. And one important question we'd like to ask and will address is, can the concolic execution be used to make this approach more robust and pinpoint the root causes of failures? Okay. Questions?
So I think in general, it's interesting to think about how what's good for your technique is good for search. I mean, in things like chess and Sage, there's a search strategy by which you search paths or you search schedules. And this has the property that you're searching, and essentially, as long as things are good, you're doing some pruning, and you're searching then a very similar. The next path or the next trace is often very similar to the previous one. So then, once you cross the threshold from good to bad, once you find a bad trace, it's very often the case that since the traces are so similar, you already get a very good candidate root cause because of the search strategy, because you're already close to a good trace when you find the bad trace. So I think it's interesting to think about, search and what the notion of closeness is and similarity, because I think in some cases you're randomly generating tests, or like in CBI, you just leave it up to the users to generate good and bad tests. And then you don't have necessarily the notion of closeness. But in search you do. You get it sort of for free, and it really helps, in our experience, I think, that you get the root cause almost for free if your search strategy has nice properties.
Okay. So one way maybe to see how the execution part is different between different runs to find out the closeness between the inputs.
Other questions? Let's thank our speaker.
Okay, thank you.